Hi, welcome to the final set of sessions for the IEEE VR 2020 conference this year. It's been quite a week. Uh, this is the track 3 on AR and perception. Uh, Before we get into details, I just want to thank all of the organizers, session chairs, authors, presenters for making this a really, really wonderful week. Uh, Obviously, the unsung heroes of this week are the volunteers and student help that most of you don't even see. If you've been an author or a session chair, or if you've been in the hubs, you've seen uh, these great students everywhere making this happen. So let's be clear, none of this could have happened without them. And so thank you very much. In fact, maybe you heard that Kai got canceled because they couldn't necessarily pull off the virtual conference, but we can. So thank you guys. Looking back now on to the session on perception and AR quickly, this year we had a number of sessions that touched on perception. We had a workshop on perception and cognition in AR and in VR, and I'm really happy to be part of wrapping up this week looking specifically at issues related to perception and augmented reality. So with that, we'll kick off our first talk, and we'll have questions afterwards. Thank you.
Good morning. Thank you for attending my talk. Today I will be presenting my paper, Archie, a user-focused framework for testing augmented reality applications in the wild. It was written in conjunction with Dr. Haiben Ling from Stony Brook University and Dr. Chu Tan from my department at Temple University. Our initial discussion will revolve around current methods for testing augmented reality systems and the limitations thereof. I will then introduce our proposed solution, Archie, and describe its system design. We will then move on to a discussion of the evaluations we conducted against Archie and the results we gathered. Finally, we will close with a discussion of the future work planned for this system. It is well understood that transitioning your system testing from the lab to the wild is a touchy process. Testers have effectively unrestricted access to the system under test, exposing it to behaviors and environmental conditions that cannot be controlled or predicted. In the wild, testing is also typically much longer in duration than lab testing, so the system under test must be stable enough to support sustained, unsupervised use for days, weeks, or months at a time. During this time, testers can encounter a wide range of issues which negatively impact their user experience. However, the underlying cause of such issues is not always readily apparent. For example, this application is attempting to identify stop signs, but is displaying an incorrect label. The cause of this error could be environmental, such as poor lighting or viewing angles, or an internal logical error in the application's object recognition model. The application could also fail to recognize a target due to limited processing resources, a particular limitation when the tester tends to move quickly through her environment. Even if an application recognizes a target correctly, the way in which the resulting label is displayed can still negatively impact the user experience, especially if it covers up crucial real-world content, such as this car moving through an intersection, or is poorly formatted for its background, such as this white text against a brightly lit sky. Even though these are simple examples, they showcase how tightly coupled a tester's user experience is with the context in which he or she is using it. One scheme of label formatting and placement may be perfectly acceptable in one situation and completely unusable in another. Our motivating goal then becomes finding a way to collect usability feedback from testers in the wild in such a way that allows us to tie the tester's feedback back to the system and environmental context that precipitated it. To guide the development of our system, we first conducted a survey of contemporary AR research efforts and cataloged the details of their interactions with human testers. Based on our survey, we observed that more than 80% of papers utilized either questionnaires, interviews, or a combination of the two in order to collect feedback from their testers. We also observed that a majority of papers conducted the entirety of their evaluations over the course of a single day, or with 25 or fewer testers. Additionally, we noted that over a third of papers explicitly tested some aspect of the system UI, including gathering tester preferences and comparing between multiple options. From this survey, we conclude a number of things. First, current research efforts are focused on manual collection of user feedback, typically after an evaluation is over. This means that researchers have no means of tying feedback back to the runtime context or recreating the circumstances that precipitated poor feedback. Second, evaluations are conducted in short durations with small groups of people. This is a limitation, particularly for systems evaluating testers' UI preferences, as snapshots of feedback in controlled environments do not necessarily extend to how a tester would respond to the system in a natural environment over time. We therefore propose Archie, the augmented reality computer-human interaction evaluator. Our solution is a framework for collecting tester feedback in conjunction with system state and environmental context data, thereby supporting system testing in the wild. Our framework consists of two main parts: a core library incorporated into the AR application under test, and a companion annotator application which can be deployed onto our helper device of choice. For the purposes of this paper, we installed the annotator app on a smartwatch. The three primary components of the framework are profiles, classifiers, and configuration files. Profiles are logical instances provided to the framework for execution during runtime. They represent distinct implementations of either input or output logic for testers to evaluate. Classifiers, conversely, represent distinct machine learning or computer vision implementations. Configuration files are simple data files which tell the framework which profiles or classifiers to execute. We will go into greater detail on this shortly. Our design for Archie fills in the gaps left by contemporary testing methods. By pairing the application under test with an annotator helper app, we are able to collect feedback from testers in the moment and in response to particular system events of interest, rather than waiting for the end of the evaluation. By collecting input, output, and system state data in conjunction with this tester feedback, we can create a more comprehensive picture of the underlying causes contributing to poor user feedback. Finally, by encapsulating input and output functionality into discrete modules, we can strategically select modules to execute at runtime and provide broader testing coverage during a single evaluation. Archie collects and stores data based on internal events within the application under test. This includes system-generated classifier events such as collection of input data or generation of results by the current classifier, the details of which are stored in a buffer. When classifier results are received, the results are confirmed with the tester via the annotator helper app. If the tester confirms the results, the buffer contents are released. If the tester contradicts the results, the buffer contents are written to the device disk for later review. Archie also issues interval-based queries to the tester to collect general usability data and to attempt to identify false negatives, or events of interest that should have been detected by the application but weren't. This data is also stored in a buffer and written to the device disk if the tester's usability score is low or she confirms the presence of a false negative. Finally, Archie collects general system state data such as frame rate, frame display time, CPU consumption, and RAM consumption. This data is maintained in buffers and periodically written to the device disk. The annotator helper application allows Archie to query the tester for feedback during the course of an evaluation, rather than waiting for the trial to wrap up before collecting feedback. We implemented the annotator app on a smartwatch, but it could just as easily be installed on a smartphone or similar device. The annotator app is triggered by events received from the application under test, using communication services within the Archie core library. The annotator app serves a number of functions: confirming system events such as detecting a target of interest, identifying events missed by the system, and collecting likability or issue data. These screenshots show a tester providing usability feedback to Archie. She double taps the center of the screen to switch from positive to negative feedback, then slides her finger around the outside of the circle to indicate how much she disliked the system. She is then given a list of high-level issues which she can select or deselect to indicate any contributing factors to her poor feedback. Archie also supports strategic management of multiple UI implementations during runtime. Based on the list of profiles or classifiers provided by the developer, Archie will instantiate and iterate between the modules, exposing the tester to each one in turn and collecting usability and likability feedback. Over time, this feedback is leveraged to give more screen time to the modules the tester prefers, while suppressing those modules which the tester dislikes. We accomplished this through a modified multi-arm bandit algorithm, which rewards profiles with higher user feedback scores as shown in equations 1 and 2. To account for the potential of tester preference changing over time, we give a greater weight to responses received most recently. Once the likability score for a given module falls below a threshold, it is removed from the collection. Once the collection shrinks to a manageable size, the modules will be executed in round-robin order until the evaluation completes. This means that the system does not have to converge onto the single best answer, but can weed out the modules in which the tester has no particular interest. The profile scheduling algorithm pulls its parameter values from the configuration file, which holds settings for a number of framework operations in addition to the lists of profiles and classifiers to execute. These also include the settings for collecting data about system events, including a tester-friendly label for event confirmation and interval values for checking for missed events. We evaluated our framework according to an overarching objective, ensuring that the performance overhead of Archie is sufficiently low, such that any negative feedback provided by the tester is not due to the framework itself. To explore the impact of Archie's performance overhead, we developed 4 evaluation candidate applications covering 3 different commercially available AR libraries: TensorFlow, OpenCV, and Vuforia for Unity. The candidate apps include TensorFlow Classify, which performs general object recognition, TensorFlow Speech, which highlights recognized words from spoken conversation, OpenCV's Color Blob Detector, which performs edge detection on different pools of color within the camera view, and Drone Tracker, a multi-target tracking app. All of the applications are out-of-the-box samples from the library publishers, with the exception of Drone Tracker, which was implemented from a standard Vuforia tutorial. The test conditions we investigated were the general overhead when incorporating Archie into the original version of each candidate application and the cost of switching between increasing numbers of profiles during runtime. From a general performance standpoint, we investigated impacts to FPS and average classification time before and after integrating Archie into each application. While we would expect the device to incur increases to CPU and RAM consumption, these costs might not be observable or impactful to the tester. Conversely, a drop in frame rate or an increase in time taken to recognize targets are much more likely to be noticed by testers. When measuring these metrics before and after incorporating Archie, we observed no significant impacts to either metric. The largest drop was to FPS in the case of the Drone Tracker application, but even that app lost only an average of half a frame per second. We also examined more traditional metrics that might not be so obvious to testers, that is, RAM, kernel space CPU, and user space CPU. Similar to the UI tests, we noticed no significant impacts to most of the updated candidate applications. The only scenario in which a particular impact was observed was user space CPU consumption for TensorFlow Speech. Our assumption for this is due to the lightweight nature of the original application. TensorFlow Speech utilized only the microphone, whereas the other applications utilized the much more resource-intensive camera. Therefore, the impacts of additional processing due to Archie are more easily observed. Our third round of testing focused on the processing costs of switching between increasing numbers of profiles during runtime. In this case, the greatest impact to runtime resource consumption was to memory in the case of I/O profile switching, but even in this worst case, the change was less than 2%. Takeaways for these evaluation results are that Archie can help to collect tester feedback and system state data without significant impacts to UI or resource consumption metrics in camera-based applications. It can also help manage module swapping with increasing numbers of profiles with only negligible performance impacts. While our original design for Archie focused on AR, the design could easily be expanded to include VR systems as well. We expanded our original motivating survey to investigate VR systems, and from this we observed not only that every single paper conducted all testing in the lab, but also that every paper but one used questionnaires and interviews to collect feedback. We also observed that 25% of the papers also investigated UI comparisons. This makes the prospect of adapting Archie for VR very appealing, but would require expanding the configurability of feedback questions and sensor integration to support collection of data on topics like simulator sickness. Additional future directions for Archie include conducting more formalized user studies with both developers and testers, as well as investigating applications of alternative feedback methodologies, such as voice commands. I would like to thank my advisor and my committee for their continued support in this research effort. If anyone is interested in talking more about this topic, please reach out to me via email. Thank you so much for listening. I will now take your questions.
Thank you, Sarah. Thank you. This is obviously interesting work. Seems to fit kind of a fill a nice gap that's needed. We have a question from Slido, and I encourage everyone to submit their questions through Slido, uh, available through the IEEE website. You can link to Slido for this session there. The question is Archie publicly available, and where can you get the code?
Yeah, so Archie is on GitHub because this is an ongoing development effort for us. It's not publicly available at this time, but it will be once we get a little more polishing done. I can definitely see this being a publicly available tool very soon.
Okay, great, thank you. So another question. So you mentioned that Archie fills a gap in our ability to collect user feedback while
Yes.
using, for example, an AR interface. But there are also, well-established formative usability evaluation methods using, for example, Think Aloud protocols.
Mhm.
Um, how would you differentiate Archie's abilities to, say, these standard usability evaluation methods?
Absolutely. So part of the limitation of Think Aloud protocols or having your testers complete diary entries at the end of the day, stuff like that, is that it either A, requires the participant, the tester, to be in a lab, um, or it requires them to remember to fill out the diary at the end of the day, at which point there's no immediate tie back to the situation which would have required them or would have instigated that poor feedback. So what Archie does is it allows you to kind of split the difference and to provide that in the moment kind of uh, feedback provision that also can be associated with uh, resource consumption, internal machine learning results, stuff like that. So then when you get back to when the results come back to the researchers in the lab, when the in the wild study is over, then you have those aggregated data sets and not just a diary or stuff like that.
Great. Okay. And we have another question from Slido. What platform platforms does Archie work on?
Yeah, so at the moment it is Android, but there's no reason why it cannot extend to additional um, uh, platforms as well. So we see great applications for this in terms of like head-mounted displays, for example, which would make data entry a little more difficult because you have glasses as opposed to a more tactile smartphone kind of interface, which makes the smartwatch entry and the simplified UI of the companion app a little more reasonable, especially for somebody with an HMD. But at the moment, it is Android.
Great. Okay, well, in the interest of time, I encourage everybody to take additional questions that they have for Sarah into Slack.
I will be there.
Great, thank you, Sarah. And with that, we'll prepare our second presentation. Okay, our next paper is being presented in Hubs, and I want to congratulate our author for taking the initiative to do that. It's quite brave and quite exciting. So our next speaker is Mati Poke. We'll be speaking on the plausibility paradox for scale-down users in virtual environments. And Mati is a postdoctoral researcher at the Center for Ubiquitous Computing, the University of Oulu in Finland. Take it away, Mati.
Thank you. Thanks, Joe. I encourage everybody, if you can, join me directly here in the hubs. I'm gonna try to show some stuff around the room, but if you want to stick where there in the viewing rooms or in the Twitch stream, that's also okay by me. So I'm going to talk about our study called the plausibility paradox for scaled down users in virtual environments. So you've probably seen some movies like The Incredible Shrinking Man, or maybe the like Honey, I Shrunk the Kids and similar, or maybe playing some video games or watching TV shows where the characters have been artificially reduced in size. You probably also seen these characters interact with their environment, like for example with needles or matchsticks or Legos or something like that. And when we actually, and they can also like maybe swim in puddles of water or something like that. When we look at how these interactions are taking place, we actually notice that they are not physically realistic. They happen as if the characters were human-sized and the environment was large instead. So, for example, if we imagine how that cat over there is knocking that Lego character down on the floor, we can imagine that the Lego character is dropping down pretty quickly. And however, if that was a human character in some kind of animation or maybe some movie, we can imagine that the character would be falling down as if it was a huge cliff, and the guy would be, or he or she would be falling down like, I don't know, tens of meters, 100 meters, or something like that. So through virtual reality, we can actually experience these kind of things, like experience this, for example, how to be artificially reduced in size. And many previous research has actually already found that we humans actually do indeed consider ourselves as normal and the environment usually abnormal when we are reduced in size or scaled up or down. Especially our body is a strong cue on that, like or parts of our body, like our hands, are actually a really big size cue for us when judging mismatching size cues. And so why should we care about these things? Well, there are actually many applications for scaling persons up or down. We have multi-scale collaborative virtual environments which allow users to interact in multiple scales and doing design and collaboration work in there. And there are even applications using both AR and VR, using like where people can interact in multiple scales. And also outside of virtual environments, we also have multi-scale robotic teleoperation in medical and other domains as well. So in this study, we were focusing on scaling the user down by a factor of 10. So making it about like size, not quite Lego size, but action figure size, like about like yay big, size of an action figure or Barbie doll. And when we're scaling virtual characters, we have this bunch of properties that we can directly manipulate. Well, viewpoint height is maybe one of the most obvious ones. Like if you scale yourself up or down, your viewpoint height goes up or down. And the virtual interpupillary distance also is a very interesting thing, and we can adjust that if our users are wearing HMDs. So the interpupillary distance actually greatly affects our perceptions of sizes and distances, like shown in the previous research I was mentioning, the previous size. And if we have some kind of representation of our virtual body, we can also change that in size as well, like or parts of our body. And similarly, we can also directly manipulate interaction distances, simulated strength, interaction domain, and locomotion speed. And that when we then change user sizes, then the perceptions change. Perceptions of object sizes changes, perceptions of distances, and even our self-image can even be changed if we the scaling operations are depending on how they are done. And also our perceived ability to act changes similarly, like can I move this book or can I throw that object and so on. And so reason I actually chose this particular room for the presentation, even though it's kind of the basic template one, is that this room where we're standing right now actually has some nice familiar size cues. So for example, the window sizes are like very much they're familiar to us. We kind of can easily imagine the size of everything in this room right here. Right now, we have these floorboards and windows and door sizes and everything. And also, if you wing this in hubs, you can probably see other characters as well. And they are also actually a really heavy familiar size cue as well, because we also judge the kind of dominant scale of things among other people also in the same virtual environment. And in this study, we're focusing on the perception of physical phenomena, and more specifically, we wanted to see, are the users perceiving realistic physics actually realistic or not? How are they perceiving, what kind of physics representations do they think is realistic or matches their expectations in virtual reality? So that makes it a plausibility study. So we didn't focus here in our study on virtual humans or other kind of acknowledgements from the environment like in other possibility studies, but we were focusing now specifically on the behavior of virtual objects and the matching of expectations. And our assumption was that realistic approximation of physics in small scales for small scale users does not match the user's expectations. So how did we do this? How did we study this? We made two conditions: true physics, which was rigid body dynamics corresponding roughly to interaction at dual side scale, and movie physics was rigid body dynamics at normal human size scale, taking inspiration for the movies I was talking about earlier. And specifically, our hypothesis was that for a scaled down user, movie physics is more likely to feel realistic than true physics. And for a scaled down user, movie physics is more likely to match users' expectations than true physics. So we set up our experiment in the virtual environment that was based on our university campus main hallway. We took some measurements of a bunch of things surrounding and around there in the hallway and put them as props in the virtual environment. So for the both conditions, we gave the visual illusion of the scaled down user acting in a normal sized environment. So you can also kind of see the low polygon representation also over there if you can see it on the desk. So and we developed it with Unreal Engine 4.22. And for the true physics condition, we just simply relied on the built-in NVIDIA physics simulation to provide us the correct rigid body dynamics when the user and all of its properties were scaled down by a factor of 10. However, for the movie physics, we employed a normal-sized user, and we just scaled the environment up by a factor of 10 instead. So this way, we had in the true physics condition, we had the realistic approximation of physics, short perceived accelerations, quick, and for the movie physics, it was like normal, like operating at the human scale. So the task was to try dropping and throwing some virtual pull tabs, and we had 44 subjects, pretty roughly equal 23 females, 21 males, and our subject ages were from 19 to 66, mean and median ages being 30 and 26 respectively. So we had a within subject design, so with gender counterbalance conditions, there was roughly the same number of males and females starting with either condition, and the subjects were using Oculus Rift S with touch controllers, and we used the Oculus setup to set the virtual IPD at 64.5 for males and 62.5 for females. And in the true physics condition, obviously, we also scaled this down by the factor of 10. We could now take a look at the video. If the video guy can also take a look at the screen over there on the right, I'm gonna show a video how the actual conditions looked like. So in the true physics condition, we can see that the objects are dropping down pretty fast because they're delta sized, and also the objects can't be thrown very far because real human hand motions were just scaled down by a factor of 10. We didn't have any simulated strength over there, but it was just the hand movements that were scaled. And in the movie physics condition, we can see that the tabs are falling down much slower, and they can also be thrown far and wide like this because the velocity that the user could impart on the tabs was big because he was like they were throwing frisbees or something like that. The tabs are also bouncing along nicely if you look at how they are thrown over there like that. Okay, now back to the slides there in the front. So after performing both conditions, the subjects were then faced with these two forced choice questions. Thinking back how the pull tabs were behaving in the experiment, which felt more realistic, like what would happen in the real world if you had been shrunk down the first or the second time, and thinking back how the pull tabs were behaving in the experiment, which match your expectations more, similar to what would happen in the real world if you had been shrunk down the first or the second time. And also after both of these four choice questions, there was also an open question simply asking why, like why did they chose the way they did. And in addition, we also made subjects to respond to a bunch of Likert questionnaires, which were asking about the properties of the flight of the pull tabs. And after that, they also responded to the Slater Usual-Steed presence questionnaire, and also we collected some background information like age and educational background and experience in gaming and virtual reality. So as for the results, around three out of four considered the movie physics to be more realistic. And also 9 out of 10 considered the movie physics that was matching their expectations better. And also the open-ended responses kind of confirmed that the almost all of the subjects chose their preferences because how the tabs were behaving, the physics conditions. There was also 6 responses that did not mention physics as the reason, and 5 of those were related to learning to use the controllers. Like they were all subjects who were starting with the true physics conditions, and they mentioned that they liked the second condition better because they had learned how to use the controllers. And as for the Likert responses, these are bipolar, so 4 is closer to realism over there. So the falling speed of pull tabs and the distance to pull tabs when shown, we can see that the movie physics was really favored over there. They were considered much more realistic and instead of the true physics. However, for the L2, the speed of pull tabs when shown, the median response is the same in both, actually, in both true physics and movie physics. However, if we look at the distribution of the true physics, we can see that the distribution of the results was all over the place, and I'll be getting back to this soon. However, this L4 and L5, the way the pull tabs were bouncing when thrown and the impact of gravity on the pull tabs, these were unipolar, so responses closer to 7 indicate preferences on realism. So here we see that the movie physics are clearly favored, being considered to be the more realistic responses, realistic simulation. We also, similarly to a possibility study to do by Scarbase and collaborators, we took some example from there. I also we split the subjects into high and low presence groups according to their SUS count scores. So, and we then checked out if this being in a high or low presence group had any effect on the responses. However, we didn't find any kind of like effect there. So it seemed that they were pretty evenly distributed in the distributions were the same in both high and low presence groups. Also, we checked the effect of demographics and also using the SUS scores and SUS counts just roll like that as predictors and see if they can also have any of these these things have predictive capability. And for the educational background, we split the population into 2 pretty evenly sized groups, and the groups were natural sciences and engineering and social sciences. Then we also used the gender and age, also VR and gaming experience, and also the SUS scores, like I mentioned, and use them as predictors. However, we didn't find any significant effect on responses on any of those either. So we couldn't really explain if these we could according to our findings, these things didn't really matter according to the responses. As a side note, there was also so there were some interesting responses on perceptions of mass and strength. So there were some subjects who mentioned that the tabs were kind of feeling heavier in either condition. We're not really sure if this was referring, if the subjects were just meaning that the tabs were seeming heavier, or if there was actually some kind of pseudo-haptic phenomenon going on there, like an actual feeling of heaviness. We don't know that, so that's something we have to look on. Check into the future. And some subjects were also contemplating on like how much strength would one need to like be able to throw the pull tabs this far or that far. There were some minor thoughts on that. However, we didn't have any kind of muscle strength simulation, but all the tab flights were simply based on the actual hand movements and in either scale, either in human scale or in doll size scale. So we did, according to our results, we did find a strong paradox concerning the plausibility illusion for scaled-down users when they're performing in physically simulated interaction in virtual environments. So the responses indicate that the subjects indeed did consider by far the movie physics to be the realistic representation of physics, and almost for everyone, even if they were kind of thinking that they believe that the true physics was the true one, it was still surprising to almost everyone in our study. So the matching of they really, the movie physics condition was the one that were matching their expectations. So the open-ended questions and the Likert responses also further imply that the subjects they really their perception of realism was indeed because of the physics properties of the taps, and there was not something else that would have messed up the responses in regarding to a plausibility illusion. We didn't find that the background VR gaming experience or the presence as in a place illusion. We didn't find any kind of explanation from these properties on why somebody would pick the other way around. And we believe that this paradox we found might have some implications on some actual areas, like for example, small-scale robotic teleoperation. Thinking about maybe maintenance robots that you would have to operate in small scales or small spaces, or maybe even some medical telesurgery teleoperation, or maybe even virtual environments where the realistic representation of physics is important, and maybe microelectromechanical systems, for example, might be an example of those, or some other kind of design collaboration task where you, for one reason or another, you want to operate in multiple scales, and you need the realistic representation of physics. And we also believe that this paradox simply amplifies the further the scale of operations deviate from the human scale. So if we go further down, we get some additional physical phenomenon going on. Static electricity or frictions become more dominant, and maybe van der Waals forces or something like that. And simply we could just get more and more of these weird physics things going on that our humans are not really used to dealing with. And we did have some limitations. So for example, the responses to L2 were kind of different from the other Likert questionnaires. And we think that the reason for that might be that with the wording of the question L2 was kind of poor. We're talking about the speed of pull tabs when thrown. So what we kind of wanted to ask was the time of flight. However, I think there was probably some respondents who thought it was as considered it like a time of flight, and there might have been also some respondents who thought it was like a speed of the object when leaving the hand, because it didn't go very far, then the speed was not very fast. So that's we think that's probably poor wording over there. That is the result of the distribution being kind of weird. And there were also so the subjects we had the learning effect there at least a little bit in some responses. The subjects that were starting with true physics were not just sure if they knew how to use the controllers instead of even though it was just a physics simulation that was preventing them from throwing the tabs very far. The experimental apparatus had some limitations. The lighting was a little bit different, not exactly the same, almost the same in both conditions. And this can be probably, if we just in the future do the physics simulation a little bit different way, we can probably get over this pretty easily. And also there were a couple of physics bugs that's happened when the tabs were behaving a little bit like the way they shouldn't be behaving. And also not all subjects really were paying attention to the flight of the tabs. So we want to make this differently in the future by just giving a little bit better instructions on how to perform the tasks. So now all of the subjects didn't really pay attention to the how the tabs were actually behaving in either condition. So in conclusion, we identified a new phenomenon. When users interact with simulated objects in a virtual environment where the user is much smaller than usual, there's a mismatch between the object physics that they expect and the object physics that would be correct at that scale. And we argue that our findings have implications for many virtual reality and telepresence applications that involve operation with simulated physics or actual physical objects in small scales. In the future, we want to also check out other scales, going further down, further smaller and smaller, and also maybe going bigger for a change. And also, we want to look at other physical phenomena besides just simple showing of just rigid body dynamics, like for example, the static electricity and stuff that I was talking about earlier. Also, right now we had this really simple interaction task, but we want to look some other type of interaction tasks that might be relevant for some kind of actual operations, and see how these kind of physics perception mismatches then affect these kind of interaction tasks. And right now in this study, we had the hands as a kind of a simple body cue, but we didn't really study the body scaling effect and how it affects the perception of physics, because it's really significant in other these kind of abnormal scale studies. So it's like pretty obvious that we want to also check how it affects our case over here as well. So here's the references that I was using for this presentation, and just thank you. Now I guess I'll hop into Zoom now and to respond to some questions. Thank you.
Okay, thank you, Matti. So we've got a question from Slido. This is from Bobby Bodenheimer at Vanderbilt. So we're a bit confused by all the scaling. In the true physics condition, was the behavior of objects the same as what would actually occur in the real world, or what would happen in a physics engine?
Of course, we're talking about the approximation of physics as simulated by a physics engine. So we're relying simply on the Unreal Engine built in NVIDIA, rigid body dynamics offered by that. So we're trying to maybe clarify the paper that it's an realistic approximation of physics, but just what would happen when interacting dual-sized as interpreted by a physics engine. So there's nothing beyond that. Maybe in the future, yes, but not here.
Okay, thank you. And another question. So would you expect the properties of, for example, the VR display, such as the field of view, to affect participants' perception of scene physics, especially at scales that are maybe more subtle? Or is our perception of physics, gravity, so strongly ingrained within us that display properties in our scale don't really matter?
I don't really, we didn't study, we didn't really think of how the field of view, for example, might affect these things. We were kind of expecting that it would be indeed ingrained so severely that that it wouldn't matter in this case, but it would be something would be interesting to check out anyway in the future. I really want to look into all these things that might affect, and especially if there are some things that would indeed help perceiving these physics mismatches, then it would be really interesting to find these kind of things. So we think that, yeah.
Especially at really small scales, right? So when you become so small that you're manipulating something that we don't normally manipulate in everyday life, you know, like an atom, what is that supposed to feel like? I mean, I'm not sure we have any kind of ground truth for that.
Yeah, those are definitely these kind
okay.
of.
There's one last question. There's a question of whether or not that you would have expected different results if, for example, you had given participants maybe a 5-minute physics lecture beforehand to prime them.
Yeah, definitely. Probably that would have affected things. Like we did really want to avoid priming the subjects in any way, so we did all that we could not to give them any kind of hints on what would be going on. But it was kind of a that's also one of the things that why we get at the educational background. If there might be some people who are more familiar with physics, for example, but in our case we didn't find any. It was too like any kind of effect on there. But yeah, we just wanted to avoid that in this case.
Great. Okay. Well, thank you, Matti, very much for the presentation. And our coordinators will now prepare our third talk of the session.
Thank you. I'll be in the hubs room.
Great. So our next speaker will be talking about the role of viewing distance and feedback on affordance judgments in augmented reality. And we're joined by Holly Gagnon, a graduate student in cognition and neuroscience, Department of Psychology at the University of Utah.
Hello, everyone. I'm Holly, and today I'll be presenting on the role of viewing distance and feedback on affordance judgments in augmented reality. So augmented reality has the potential to enhance human performance in many tasks and applications. Recent use of AR has been demonstrated in areas such as interior design, healthcare, entertainment, and navigation. However, the effectiveness of many of these applications is influenced by the extent to which users perceive that they can act on virtual objects as if they were real. There are important limitations to consider with AR technologies that might influence these judgments of action capabilities. One challenge is the limited field of view, which restricts the extent of the virtual features that can be viewed at one time. A second challenge is how to provide feedback about action when observers act on objects that do not actually exist in the real world. So in the study today, we'll address both of these challenges. Action possibilities within an environment that are scaled to an observer's body or their ability to act are referred to as affordances. Two common examples of affordances that have been studied in the real world, in virtual reality, and recently in augmented reality are stepping over and passing through. So when deciding whether you're able to step over a gap, you'll consider the length of your legs. When evaluating whether you can pass through a doorway, you'll consider the width of your shoulders. By comparing the perception of affordances in AR to the established affordance perception in the real world, we can see how similar perception and action are across real and mediated environments. This information can then be used to inform the design of effective AR environments. In the current study, we'll focus on the affordance of passing through an aperture or doorway. Previous research in the real world has shown that when observers make judgments about passing through an aperture, they consistently allow for a margin of error that is 16% greater than their actual shoulder width. This finding is consistent regardless of the observer's body size. Similar results have been found in VR, and there have also been initial results in AR that suggest passing through affordances are similar to the real world. However, in these studies, participants usually stood about 3 meters from the aperture to make their judgment, allowing them to see the entire aperture within their visual field, like the augmented poles pictured here. Although passing through affordances in AR appear to be similar to the real world, stepping over affordances are different in AR compared to the real world. So why would passing through be similar while stepping over is different? It could be due to the field of view. In the real world, when making a stepping over judgment, as pictured here, the participant can see the entire gap within their visual field. But due to the limited field of view in AR, pictured here, only a portion of the gap is visible at once. As a result, making the stepping over judgment requires the observer to move their head and integrate visual information over space. This could affect perception of size and distance, as well as just make the task more difficult overall. In the present study, we'll see whether limiting the amount of visual information about an aperture affects affordance judgments of passing through an AR. Previous work has demonstrated that people can improve their affordance judgments by physically performing the action and subsequently receiving perceptual motor feedback. However, feedback in the resulting calibration of action judgments has yet to be explored in AR. Providing feedback in AR can be a challenge because users do not receive haptic feedback from, say, bumping into a wall, and it may also be difficult to receive effective visual feedback because it can be difficult to see whether you're actually colliding with an augmented object. So, how can we effectively provide feedback in AR? In the current study, we'll investigate whether verbal feedback alone will improve passing through affordance judgments in AR. To address the perceptual implications of the limited field of view and difficulty of feedback in AR, we varied 2 factors in a passing through task using the Microsoft HoloLens. First, we asked whether viewing distance, which directly correlates to the amount of the aperture that appears within the field of view, influences the accuracy of judgments. As you can see here, standing close to the aperture makes it difficult to see the entire aperture within the field of view, whereas standing at a farther distance, it's easier to see that entire aperture within your field of view. And then second, we asked whether judgments could be improved as a result of verbal feedback that is not reliant on physically walking through the aperture. We had 3 hypotheses. First, we predicted that at the farther viewing distance, passability judgments would be more closely scaled to participant shoulder widths, since it's easier to see that entire aperture. Second, based on previous research, we predicted that overall, judgments would be initially overestimated and then would reduce in error as feedback trials progressed. And then our third hypothesis was that we predicted that this error reduction would occur at both viewing distances. So viewing distance was manipulated between subjects so that each subject either saw the aperture at a near distance that was less than 1 meter, or they saw the aperture at a far distance, which was at about 3 meters. All participants completed 2 different types of trials. In adjustment trials, participants adjusted the virtual aperture until they felt that it was the smallest aperture that they could pass through without turning their shoulders. They adjusted the aperture by using the vocal commands bigger or smaller. In feedback trials, participants were presented with an aperture and asked to judge whether they would be able to pass through it or not. After they said their answer, they were provided with verbal feedback via the headset on whether they made a correct or incorrect judgment. If they made a correct judgment, the headset said correct, and if they made an incorrect judgment, the headset said incorrect. Participants completed adjustment and feedback trials in a specific order. First, they started out completing 4 initial adjustment trials, which I referred to as block 0. Then they completed 4 blocks that had the following progression. So each of these blocks started with 2 feedback trials where participants judged whether they could pass through an aperture presented at a specific width. Then they completed 2 adjustment trials, then 2 more feedback, then 2 more adjustment trials. So this pattern of 2 feedback, 2 adjustment, 2 feedback, 2 adjustment was repeated for each of the 4 blocks. We chose to repeat this procedure over a number of blocks in order to track the time course of the effect of feedback. And although this might seem like a complex procedure, it is the same as many other feedback and calibration studies conducted both in the real world and in VR. We analyzed the data using the aperture widths that the participants set during their adjustment trials. We divided the set width by their actual shoulder width to create a ratio. A ratio of 1 would mean that they set the aperture exactly at their shoulder width. A ratio greater than 1 means that they set the aperture wider than their shoulder width, and a ratio less than 1 means that they set the aperture smaller than their shoulder width. We collapsed these ratios by block, resulting in each participant having 5 ratios. We then use these ratios to conduct a repeated measures ANOVA, and as well as plan comparisons to compare blocks. Our first hypothesis was that passability judgments would be closer to participant shoulder widths at the far viewing distance compared to the near viewing distance. However, we actually found the exact opposite. There is a significant between subjects effect of viewing distance such that affordance judgments were actually closer to participants' shoulder widths, meaning that their ratios were closer to 1, at the near compared to the far viewing distance. In the graph here, the average ratio is presented on the y-axis and the block number on the x-axis. There's a bold horizontal line at a ratio of 1.16, which is the traditional finding of passability judgments in the real world. Near distance judgments are depicted by the red triangle line here, while far distance judgments are depicted by the blue circle line here. And the error bars are within subject error bars indicating plus and minus 1 standard error. So the red line indicating the near distance judgments is closer to the ratio of 1, indicating that affordance judgments were closer to participants' shoulder widths at the near viewing distance. And I'll discuss why this might be in a little bit. Our second hypothesis was that judgments would initially be overestimated and then decrease in error as feedback trials progressed. And our third hypothesis was that this reduction in error would happen at both viewing distances. We did find that overall, affordance judgments were overestimated. So both the near and the far viewing distances had mean ratios greater than 1, indicating that participants allowed for a margin of error in their passing through judgments. However, feedback was only significantly reduced in error at the far viewing distance. Specifically, error decreased between block 0 and block 1, and between block 1 and block 2. After the second block of feedback trials, the judgments remained consistent. The near viewing distance did not have any significant reductions in error. A possible explanation is that participants were already quite accurate in their initial affordance judgments. And the fact that their affordance judgment ratios did not decrease further provides support for the notion that people perceived the AR aperture as they would in the real world. There is a slight increase from the third to the fourth block, which might be due to fatigue or regression to the mean. Finally, a post hoc multivariate ANOVA indicated that performance between the far and the near distance did not differ after the second feedback block. So they differed for the first 2 blocks, but not after the second feedback. So why were passability judgments initially better at the near viewing distance? One reason could be that participants used a strategy not based on body scaling. So instead of thinking about their shoulder width, they might have used visual comparisons of the aperture that fit within the field of view. So when you use the HoloLens, it kind of feels like looking through a window. You see the real world around you, but you only see the augmented objects within a distinct frame. And participants could have used this frame as a reference point. For example, if they remembered that they made an incorrect answer when the walls were presented at this aperture, but they made a correct answer when the walls were closer to the edges of the frame, they might have been using that relation between the aperture width and field of view frame to make their adjustments rather than their shoulder width. Another possibility could be due to the interaction of distance and size perception. Preliminary research indicates that distances might be underestimated in AR, so if distance was underestimated at that farther viewing point, the size of the aperture might have been perceived as smaller. As a result, observers would have had to set a larger aperture to compensate for this underestimation. However, this is a speculative reason because we didn't actually collect measures of distance perception in the current study, but this is something that could be collected in a future study. A primary goal of the study was to test whether relatively simple verbal feedback given to participants about the match between their affordance estimates and their actual shoulder widths would change their responses. And we did find support for this. Participants calibrated their responses by the second block of feedback. This suggests that verbal feedback, which might be easier to implement than other forms of feedback in AR, is sufficient to calibrate passing through affordance judgments in AR. Currently, we're conducting this same study, except instead of participants receiving verbal feedback at a static viewpoint, they are physically walking through the aperture and they receive auditory feedback on whether they would have actually been able to pass through the aperture. And we're investigating whether providing this additional motor and visual information will affect calibration differently. In the future, we think it might be worthwhile to evaluate passing through affordances at a larger range of viewing distances to test whether error increases with even farther distances in AR and whether feedback effects are replicated and similar in magnitude. I'd like to thank our collaborators and the Office of Naval Research for supporting this work, and thank you for listening and attending this virtual session.
Okay, thank you, Holly. So we do have a question on Slido.
Mhm.
I've pasted it into your chat window if you want to sort of read along
Okay.
as I read
Mhm.
it to you. Okay, is the difference between far and near judgments matching the distance perception observed for far and near distances in AR? That is, how much of the observed near-far differences might be attributed to distance misperception in AR? So I
Oh,
think you alluded to this at the end, that we know that judgments are underestimated in VR and AR, but I guess maybe the question is how much of the differences might be attributed to that, or is that knowable?
right. That's a good question. I think it is definitely possible that the distance misperception could have played a role because, as you mentioned, we do find underestimation of distance in AR. And so, since the distances are pretty different, so that close distance is less than 1 meter, whereas the far distance is that 3 meters. So yes, I think it is possible that at that 3 meter distance, there might have been more of effect of the misperception of distance.
Great. And another question, what kind of training or practice trials did you offer to participants to maybe acclimate to the AR stimuli or just to the AR environment?
Right. So we actually didn't provide practice trials. We explained the tasks in depth, and we found that it was pretty self-explanatory. Like participants could pick it up after we explained it to them. And in that initial adjustment trial as well, they had a few more adjustment trials than later on, and so they had more. I guess those were kind of like the practice trials where they could practice adjusting the aperture.
Okay, good. So another question. During the trials, did you instruct or restrict your participants' head movement, or were they able to make use of other depth cues like motion parallax to make the judgment?
Right. So we didn't restrict their head movement. We did ask everyone after the session to like see what kind of strategies they used. Specifically, we were curious whether participants would be like looking down, like at their feet more, or if they would be looking straight ahead and doing more side to side judgments. And we did see that across participants, people used both of those strategies. We haven't done like an in-depth analysis on, like if people used those in one condition more than the other. But there were some differences and in how people made their judgments. Yes.
Great. Thank you all for sending in questions over Slido. This is nice. Okay, so another question. This is from an anonymous person. Did you also look at the effect of horizon scaling? Namely, when the observer is closer to the aperture, could the effective horizon scaling information also diminish?
Good question. So we tried to minimize the amount of information in the background, so behind the aperture. So we like put blue sheets up on the walls, and it was a relatively small room, so there wasn't much of a horizon for them to um, use, I would say. So it could have an effect, but I think we tried to minimize that as much as possible.
Sure. And this is actually my question because I haven't seen this, but maybe I'm sure it exists, right? I can't see everything. Are you aware of it, or have you thought about a real world control condition where, for example, you have movable walls to see how the AR perception of affordances might compare?
Right, for sure. We have thought about it. We wanted to like just see the feasibility of it in AR first, but we think doing it in the real world would be cool because then we could also manipulate field of view a bit more as well. So we do think that could be a future direction. Yes.
And you mentioned that's the strategy that some participants might have taken by using the framing of the field of view of the HoloLens. Clearly, you can, like as you mentioned, you can manipulate that with some kind of shuttering or
For sure.
occlusion mechanism. Yeah, no, that would be very interesting.
Mhm.
Okay, just checking for other questions. Yeah, I think we're getting back on time, so this is probably a good time to wrap up. Thank you, Holly, so much.
Great.
And we'll move on to our next speaker.
Yes, thank you.
Okay, great. So we're back, and we have another paper on glanceable AR. You might have noticed that there was a paper from the same group presented earlier, or by the same larger group at Virginia Tech. This is on evaluating information access methods for head-worn augmented reality, and the presentation is by Fei-Yu Liu, a PhD student at the Department of Computer Science and Center for Human-Computer Interaction at Virginia Tech. Fei-Yu, you have the floor.
All right. Thanks, Joe, for the brilliant introduction. Good morning, everyone. My name is Fei-Yu. I'm a second-year PhD student and a member of the Center for Human-Computer Interaction at Virginia Tech. Today is my pleasure to be here and present to you our paper entitled Glanceable AR, Evaluating Information Access Methods for Head-Worn Augmented Reality. Before I start, I would like to thank my colleagues, Shakiba, Li Yuan, and my supervisor, Dr. Bowman, for their continuous guidance and support throughout the project. So first, let's talk about motivation. So we encounter a variety of information needs every day. We need information about the weather, our to-do list, our calendar events to determine our arrangement and executions of everyday activities. And mobile phones provide convenient ways of obtaining information, but they could be cumbersome when our hands are occupied by other tasks. And smartwatches guaranteed high accessibility of information as a wearable device. However, they could only convey a limited amount of information at any time due to their limited screen size. And meanwhile, AR head-worn displays has been long imagined by previous researchers as devices that will ultimately become much like, or even replace mobile phones as a future way of obtaining general information. Future AR users could be wearing AR glasses all day, interacting and viewing virtual information to assist their personal computations. And with the recent advancements of AR head-worn displays, we are getting closer to the envisioned future than ever before. And previous research has explored AR as a possibility to display general information. For example, AR Win is a system that overlays virtual information on the top of a real-world desktop, but the strict word-fixed layout does not allow mobility of the information. And recent research by Legis and Bowman on adaptive walking interface has shed light on how AR can allow users to bring their workspace with them while walking. And their result especially emphasized that it is important that the virtual content does not block users from seeing the real world behind it when the users want to. So because AR head-worn displays, unlike current mobile or wearable devices, are worn on the head and always visible, how to present information in an unobtrusive but easily accessible way still remains an open question. So in this research, to fill this gap, we propose glanceable AR, an interaction paradigm for accessing information in AR head-worn displays. And according to Matthews et al., glanceable interfaces allow users to access and understand the information quickly with a quick glance. And we distill 4 design principles based on previous literature on AR information display and peripheral awareness. The first design principle is the virtual content should be fixed to the user to ensure high availability of the information. The second design principle is the virtual content should be specially distributed in the periphery to alleviate the problem of information overload, and user can use their special memory to access the information they need. The third design principle is the interaction to access the virtual content should be hands-free because our hands are very likely to be occupied by other activities in our everyday scenarios. And we think head-based or gaze-based interactions are promising ways to interact with future AR head-worn displays. And the last design principle is the information should be accessed by glancing quickly at the periphery because glancing allows us to understand information without being noticed by other people, which we think could be beneficial in protecting privacy and lead to an increased social acceptance. We propose 3 interfaces under the glanceable AR paradigm. The first interface we propose is called the iGlance interface. So even though we call it iGlance, it does not involve any eye tracking. So the interface itself is very similar to a heads-up display in which the content they are display fixed and they reside at the periphery of the field of view of the AR display. To access the information, users just need to simply turn their eye to look at the content, which is why we call it iGlance interface. And the interface is always visible, which ensures high awareness of the information, but also the information could be cluttered and occlude users from seeing the real world behind it. The second interface we propose is called the head glance interface. In the head glance interface, the contents are fixed to the body orientation and they are not invisible initially because they are distributed in the periphery. And if the user is looking forward, which means that the user's head and their body share the same orientation, they won't be able to see the virtual content. But if they only turn their head to one side of their periphery, they can see the virtual information. For example, if users want to know something about the weather, they just need to look up at the sky so they can see the weather information. And the third interface we propose is called the gaze summon interface. So similar to the iGlance interface, the gaze summon interface is also display fixed, but contents there are initially invisible, but they're represented by little translucent visual targets. And to access the information, users just need to gaze at the visual target for 0.5 seconds to summon the corresponding information into their field of view so they can look at the information. For example, if users want to know something about the weather, they just need to gaze at the top visual target for 0.5 seconds so they can summon the weather information into their field of view to look at the information. And this is our hypothesized trade-offs of the three interfaces. So we have accessibility, which is the speed of accessing the information. We have awareness, which is the awareness of changes in the information, and unobtrusiveness, which is the ability of the interface to avoid disturbing users from doing their primary tasks. And we think iGlance interface provides high accessibility and awareness of information by making them always visible and obtrusive. And Gaze-Summon interface allows users to access information also by only turning their eyes. But the dwell technique lowers the accessibility of the interface. And awareness of interface is also low since the information is invisible initially. And the head glance interface make information highly unobtrusive by making them invisible in the forward direction. The user also have to turn their head to access the information need, which lowers accessibility and awareness. So in this research, our main goal is to validate the trade-offs among the three interfaces that we proposed in a dual task scenario. So we used the Magic Leap 1 headset and the internal binocular eye tracking sensor to implement the interfaces. And to evaluate the interfaces, we had a dual task scenario in which users have to do a primary task and a secondary task at the same time. The primary task is to walk for 2 minutes and follow a virtual human. The virtual human will be walking along a predefined path in the room, and it will be changing speed randomly. And users have to keep an ideal distance from the virtual human while walking. On the back of the virtual human, there is a color panel indicating the user's current distance from the user to the virtual human. If it's green, that means ideal distance. If it's reddish, that means too close. And if it's bluish, it means too far away. And at the same time, we will place obstacles, which are these long balloons along users' path of walking. And users have to pay attention to those long balloons, try to avoid them, step over them, not to step on them. And when they are doing the primary task, there will be a secondary task. And we have two different types of secondary tasks. The first one is the discretionary task, in which the program will be randomly asking user questions about the glanceable information. For example, the program might be asking user, what's the temperature now? And user have to refer quickly to the glanceable information and verbally say the answer. By doing this, we hope to simulate a scenario in which query of information are initiated through conversations. And we have 12 questions in the 2 minutes walking task. And the other type of secondary task is the monitoring task, in which instead of looking at the information when the program asks them to, users have to pay continuous attention to a piece of virtual information, in which, in this case, is a virtual basketball scoreboard. And users have to pay attention to the scores and report as soon as they observe a lead change in the score. And there will be 8 lead changes in 2 minutes walking. And we recruited 18 participants, 4 females with a mean age of 20 years old. And we used a within subject design. We have 3 interfaces, iGlance, headglance, Gaze-Summon, and we have 2 different types of secondary tasks, the discretionary and monitoring task, yielding a total of 6 different conditions. And the whole experiment took 60 minutes in total. So to measure the primary task performance, we had a distance keeping score in which we counted how much time users spent in too far or too close regions to the virtual human. So the lower the distance keeping score, the better the performance. We also counted how many balloons the users were not able to avoid. And to evaluate the secondary task performance for discretionary task, we measured how much time it took for the user to answer a question after one was asked by the program. We also measured how much time it took for the user to report the lead change after one actually happened in the interface. And for subjective feedback, we had system usability scale questionnaire, we had NASA TRX workload questionnaire. We also had a post questionnaire asking users about their thoughts, their opinions about each interface in each condition, what they like or dislike. And to allow a more comprehensive qualitative analysis, we also implemented a playback system in which we logged user head position, head orientation, gaze direction, and virtual human position 10 times per second. So we were able to reconstruct the whole walking experiment for later analysis of user behaviors. And we tested 4 hypotheses in this user study. The first hypothesis we tested is we think in the discretionary task, head glance and Gaze-Summon interfaces will be more preferred, and they could lead to better walking performance compared to iGlance interface, because we think head glance and Gaze-Summon are very unobtrusive, which allow users to focus on the walking task itself. And this is our result. Our result did not support hypothesis 1A because the preference on the interface were pretty much distributed in the discretionary scenario. And we also did not find any significant difference in the walking performance, which did not support our hypothesis 1B. And in the second hypothesis, we think that in the discretionary task, head glance and iGlance interfaces could result in significantly higher information access speed than the gate summer interface because of the 0.5 second dwell time in the gate summer interface. And our results support this hypothesis by showing that head glance and eye glance result in significantly lower time to access the information. And in the third hypothesis, we think that in the monitoring task in which users are asked to pay continuous attention to a piece of basketball scoreboard, head glance and eye glance would be more preferred and lead to better walking performance because the eye tracking feature of the gate summer interface will draw user attention away from the walking task when they monitor a piece of virtual information. And our result partially supported hypothesis 3A because we found a clear tendency towards favoring eye glance interface, but not head glance interface. And we found in the walking performance, we found that head glance user performed significantly worse than eye glance user, which also did not support our hypothesis B. And in the last hypothesis, we hypothesized that in the monitoring task, head glance and eye glance would result in significantly less time to report the lead changes compared to the gate summer interface. Because in the gate summer interface, users have to maintain their gaze at a visual target to make a content always visible, which we think would not be preferred by the users. And our result also didn't support this hypothesis by showing no significant difference in time to report the lead changes. So to conclude a bit, our results show that head glance and eye glance could lead to faster acquisition of information, and eye glance interface resulted in superior walking task performance than head glance interface in the monitoring task. And also eye glance interface was more preferred when continuous attention was desired on a piece of virtual information. So it looks like our result favored eye glance in different ways. But does that really mean that eye glance is the best interface among the three? And we don't think so, because based on the comments we gathered from participants, they like eye glance because they think it's simple, it's fast, it's easy to access, but they also don't like it because they think it's cluttered, the information is crowded, and occluding their view from seeing the real world. While for head glance interface, they like it because they think it has the best visibility of the real world by making information nearby but never in your face. But they also think head glance could be tedious for repeated usages in a short period of time. And when accessing the information in the head glance interface, they have to take their eyes off the walking task, which damaged their primary task performance. And this could be the reason why participants perform significantly worse in head glance interface than eye glance in the monitoring condition. And this is the workload. We can see that head glance resulted in significantly higher mental workload and effort and frustration than eye glance interface in a discretionary condition. And for the gate summer interface, participants like it because they think it's cool, it's futuristic, it has good visibility of the real world, and they can access the information without the need to move head or body. But they also don't like it because of eye strain, and sometimes false positive happens because the tracking is not perfect. And they also think it's not suitable for monitoring because users have to maintain their gaze at the visual target to make a piece of content always visible. And from the TLX questionnaire, we can also see that the gate summer resulted in higher mental workload and effort compared to eye glance in the monitoring condition. So when being asked whether the number of windows would affect their preferences on the interfaces, 14 out of 18 participants gave a positive response. And they think more window will make them favor eye glance less because the interface will just be more cluttered and more crowded and occlude them from seeing the real world behind it. And they think head glance interface could be a good option for having more windows because no matter how many windows they have, it will never be in their face. And they also think gate summer interface would work worse when there are more windows because there will just be more visual targets in the interface. And the reason that we think participants favored eye glance more than the head glance and gate summer interface because we think the walking task itself is cognitively easy and not demanding in the periphery, which diminished the unobtrusive advantage of the head glance and gate summer interfaces. The evidence for this is like only 2 participants stepped on the obstacle, and both of them is in the eye glance monitoring condition. So to conclude, we think that glanceable AR interfaces are still promising approaches that need further exploration. And back to our hypothesized trade-offs, we accessibility, awareness, and unobtrusiveness to discretionary monitoring and walking task performance accordingly. The eye glance interface did not result in worse walking performance, which indicates it was not that obtrusive as we thought. And we did not find difference in time to report lead changes in the monitoring condition, which indicates, although not as good as eye glance, head glance and gate summer could also provide some level of awareness of information. And head glance interfaces was proved to be as fast as eye glance in acquisitions of information, which higher the accessibility of the interface from low to medium. In contrast, the gate summer interface was proven to be low in accessibility since it resulted in significantly slower information acquisition. And these properties are only result for this working experiment, and we expect them to be different in different primary or secondary tasks. So the main contribution of this work include the glanceable AR paradigm for information acquisition in AR head-on displays, and the 3 interfaces we propose under the paradigm, and the validation of the trade-offs among the 3 interfaces in a dual task scenario. As for future work, we plan to further improve the interfaces by increasing the unobtrusiveness, but still providing efficient information acquisition by the comments we gathered from participants. And one solution we propose is called the Head Glance Plus interface, in which virtual information, they are represented by little white dots. And if the user are trying to looking behind the dot at the real world environment or people behind the dot, the information won't appear to avoid blocking the users. But if the user converts their gaze at the depth of the dot, they can trigger the information so they can look at the information. And we also think that the walking is simple and low in cognitive load task. And in the future, we plan to test the interface in a more demanding scenario that requires attention in the periphery, for example, driving in a simulator. That's all for my presentation. Thank you for listening, and I'm happy to take questions. Thank you.
Great, thank you, Fei-Yu.
Thank you.
We have a question from Slido. Why did you select 0.5 seconds for your gaze summon interface?
That's actually by iterative testing. So if the time so we need to find a good balance between speed and accuracy. If the time is too much, then that means the information acquisition would be slow. But if the time is too less, then like more false positives would happen when the user are moving their eyes. So during iterative testing, we found that 0.5 second is a good trade-off between speed and accuracy. That's why we select 0.5 second as the dwell time.
Okay. Another question for you.
Mm-hmm.
So regarding the gaze summon technique, so I'm wondering if all off-screen locations are created equal. For example, would glanceable information placed just off the top of the field of view be equally accessible or usable as glanceable information placed off to the side? Because I could see some eye or head physiology or even the task setting creating peripheral areas that are not all created equal.
Yeah, that's a very good question. We actually wasn't able to measure the differences between the time user take to access the information in different directions, because our information, some of them have text, some of them have numbers, and some of them are relatively easier to read. But that's definitely an interesting future work to explore whether there are differences in difficulties to access the information in different directions. Thank you.
Sure, thank you.
Yeah.
We have another question from Slido. Slido's got lots of questions for us. So can you compare your results to Google Glass, for example, where all information was placed above normal field of view?
Yeah, so we had the iGlance interface that we have, which is very similar to a HUD. And I believe it's also similar to the interface that Google Glass was using. Is like overlay virtual information on top of the real world. And it is always visible no matter where the user is looking at. So I think we have compared this with our head glance and get some interfaces. So for more detail, please refer to our paper. Thank you.
Okay, and one last question. You know, your work identified a lot of interesting trade-offs in those 3 techniques. But kind of wrapping that all up, can you identify a usage context where one of the methods, I don't know, head glance or gaze summon, would be most appropriate? Like a specific kind of use case?
Yeah, that's a really good question. So I think for the head glance interface would work really good when we have a primary task that is very cognitively heavy, and we don't want the virtual information to take our cognitive effort away. And okay, some interfaces could also work well in this condition, but I believe head glance is the best option. And the iGlance interface obviously is like, if you want to pay continuous attention to a piece of virtual information, you would want it to be always visible. So the head glance interface could work best for monitoring a piece of information.
Yeah, it seems like it seems like understanding sort of the demands of the primary task would help you then decide which of these supporting interaction techniques or gaze aware techniques would work well. Okay,
Yes.
I'm checking for other questions. No, so thank you, Fei-Yu. We appreciate your talk.
Thanks.
And I guess we'll prepare our last talk of the day. Okay, we're back with our 5th talk of the session on the influence of perspective on dynamic tasks in VR. This is by Naval Bhandari. He's a PhD student in the Department of Computer Science and the Center for Digital Entertainment from the University of Bath in the UK. Naval?
Cool. Thank you very much. My name is Naval Bhandari, and I will be presenting the influence of perspective on dynamic tasks in virtual reality. A little weird that I'm in the AR session since nothing to do with AR, but let's go with it. Cool. So what is a dynamic task? A dynamic task is one in which the active performance of the task is influenced directly by the changing environment in which the task is performed, which is basically just a fancy way of saying if there are internal and external elements that might affect user performance in the task. Whereas a static one is where there are no such elements influencing the task. But this means that everything could be dynamic. So there are quite arbitrary definitions of what a dynamic task is. Some papers say if your body remains static, then it's static. Others say if there's stochastic elements involved, then it's dynamic. We defer to the latter one. What is the motivation of this paper? Most studies on task performance in VR are multi-task, so they focus on one single task. There is no variance in the dynamic levels of that task, so they're just one specific basic task they have to do with good reason. You don't want to vary it depending on what task you're performing, but that gives us scope to look at different types of tasks so we can try and vary the dynamic elements in it. There are also very few studies conducted on third-person perspective. The ones that have been conducted, they're mostly non-substantive in that they are quite old. So talking about 10 years ago when the hardware was a lot more primitive, they're entirely qualitative, so they don't use any performance metrics, or they have very few participants. So having these two elements gives us good scope for a study. So for the actual experiment design, we have to choose task. We looked at sports because sports are generally inherently dynamic. Many sports have similar mechanics that are transferable from one to the other, which lets us vary the dynamic levels quite nicely. They're relatable to a real-world scenario from VR into physical world, and then vice versa. The actual 3 sports that we chose with varying dynamic elements are archery, darts, and tennis, from least dynamic to most dynamic. For archery, for the first task, we chose archery. It's the least dynamic of the 3. All you do in it is you knock an arrow, draw it, point it to where you want, and release it. That's it. So there's very little physical involvement involved. We had 9 targets placed in the environment, and as soon as you hit one, you move to a new target, and you just have to keep shooting them to hit the target. The next one, we had darts. It's very similar to archery. You have to hit a target. Again, we chose 9. It requires physical momentum of the user this time in the wrist and the hand. So instead of just knocking it and shooting it, you have to physically throw it, which involves using your wrist, and you have to vary the level of power and your release point to hit the target. So there's a bit more dynamic element involved. And the last one is tennis. We center the position of the user, and they remain static in that position. They had to hit 3 targets on the other side of the court. If you look at the picture, there is a glowing target there, and they have to hit that. That moved. We placed their equidistant spaces on 3 bits at the end, and as soon as you hit a target, it moved to one of those. There was also a tennis ball shot towards the user from those same 3 positions, giving a total of 9 positions, 9 targets to hit in total, where it's coming from a different space, and then you have to hit it to a different space. Tennis involves full body motion, so you have to move your torso, you have to move your arm to hit the ball, so it's quite dynamic. Because there are so many dynamic elements in it, that's why we centered and kept the user's position in the same place. For the perspectives, we chose 3 perspectives. The first is first-person perspective, which is your standard view in VR. If you've ever used VR before, it's what you'll use normally. We had egocentric third-person perspective, where the camera follows the head. So if you imagine This is the head, this is the camera. As you move, the camera follows behind you like that. And then we had allocentric third-person perspective. This is the head, this is the camera. They are independent of each other. If you move like this, it moves as well, so you can't see your head anymore. And this one gives you a bit more scope in terms of you can move back and forth to increase or decrease your field of view. You might not always be looking at your head. We had 9 targets, 3 perspectives, and 3 sports, giving us 81 trials per person. So what were our hypotheses for this experiment? We were observing spatial perception and performance of the user. Our first hypothesis is that first-person perspective is better than both egocentric and allocentric third-person perspective, specifically for performance. Our second hypothesis is that egocentric and allocentric third-person perspective are better than first-person perspective for spatial perception. And our third one is that egocentric third-person perspective is better than allocentric third-person perspective for both performance and spatial perception. The actual procedure, we had 30 participants. We had a full-body avatar representing the user in VR with inverse kinematics based on the head and 2 controllers. We made tennis easier by introducing a bias to the target because we had a floor effect from initial pilots where everyone was just missing the target and doing rubbish. So we introduced a bias to shift that bell curve. We observed several metrics to analyze performance and spatial perception. All of these are in the paper. For performance, we looked at things like how many times did they actually hit the target and the time that it took them to hit it. For spatial perception, we looked at the distance from the ideal location, which was the center, and if when they hit the tennis ball, for instance, how far was it from the center of the racket. For the actual results, for first-person perspective and third person, all of the metrics supported the first hypothesis for archery and dart. First-person perspective outperformed both egocentric and allocentric third person on every performance metric for both archery and dart. For tennis, the most dynamic task, the results were inconclusive. There were no significant differences between any of the perspectives. For the second hypothesis, we had different results for each sport. So for archery, our metrics rejected this second hypothesis. First-person perspective outperformed third-person perspective in spatial perception. For dart, the partial allocentric third-person perspective was better than first-person, whereas egocentric was worse. And then for tennis, both egocentric and allocentric were better than first-person perspective. And then lastly, for our last hypothesis, we had mixed results for the and users more accurate in egocentric, but they had better rotational consistency in allocentric. Okay, my bullet points are weirdly screwed up there. For darts, users in allocentric third-person perspective outperformed egocentric third person, and they had better spatial perception. And then for tennis, users had better spatial perception in allocentric than in egocentric, but the results were inconclusive for performance. So we got also interesting demographic results. Users who had moderate or greater experience in VR outperformed those who had little experience. Users who had moderate or greater experience in third-person games didn't significantly outperform those who had little experience, but users who had more experience in first-person games did outperform those who had little experience. We also conducted a post-condition questionnaire and found that users mostly preferred first-person perspective or allocentric third-person perspective to egocentric. They felt more immersed and preferred less dynamic tasks to the more dynamic tasks as a trend. So if the tasks got more dynamic, they preferred them less. They also found the less dynamic sports easier. There are a few limitations with our task. The apparatus doesn't actually match the what you'd use in the actual sport. So you're not actually holding a bow and arrow, you're not holding a dart, you're not holding a tennis racket. So obviously that has an effect. There was also the lack of physical feedback. We used haptics for when the user hit a tennis ball, but there's no actual feedback from that. And then there's also the generality issue. how much can we generalize our results to other dynamic tasks. By the very nature of a dynamic task, they are stochastic, so you have different stochastic elements, and obviously different dynamic tasks are going to vary massively. So dynamic navigational tasks will have very different observations to the ones that we've conducted. For actual conclusions, we concluded that first person perspective for static to moderately dynamic tasks is better. But if you're using a third person perspective, we recommend allocentric. And I think that's it. Thank you very much. I will take any questions. Thank you.
Okay, Naval. Thank you very much. Okay, I encourage listeners to post via Slido any questions you have. And we have one that just popped up now from Bobby Bodenheimer at Vanderbilt. In the third person point of view camera views, can you explain how the camera moves as the person moves in turns in particular?
So for egocentric, if you imagine a stick on the back of your head, you've just got a camera attached to that, and as you turn your head, the camera's just going to point directly at it. For egocentric, they're independent, so if you move right, the camera will move right. Ergo, you can't see yourself anymore, but you're not limited to just looking specifically at your head. There are trade-offs between both, they're quite different, but that's what we thought was interesting to test both against each other.
So the allocentric view was fixed, and the participants had no control over that view?
No. So it mimics the head movements, but it's not attached to the back of the head of the user. So if you imagine another body you're looking at yourself, you're making the movements, and if you turn around, you won't be able to see yourself anymore.
Okay. Just checking other questions. Okay, we have one. Does the nature of the task goal suggest which viewing paradigm might work best? So it seems like archery and darts are inherently different than tennis, right? Whereby in tennis, you first need to strike the ball correctly. And in archery and darts, that first person view of the target needs to be sort of the primary interest.
It does. It's always quite difficult with these test experiments where the task influences the results quite a lot. So we did try and be careful with what we're actually trying to achieve. You do have the extra stochastic elements with the ball coming at you, striking it and hitting it towards the target. But we thought that we wanted to make it more dynamic. The end goal is obviously the same thing. It's just trying to hit a target, essentially. You can do that so much with ones where you're just holding it and throwing it to darts is probably the most dynamic with that. You have to add additional elements in it to make it a bit more dynamic.
Okay, thank you. Any other questions? Okay, well, we are running over. So I want to thank Naval, as well as all of our other speakers and the coordinators behind the scene, and all the questions that you all sent in via Slido. Thank you. Quick note, while this session is now done, a reminder that VR 2020 is not done, right? There is much, much more. After lunch in particular, there's posters and videos over in Hubs starting at 1:30 Eastern Daylight Time, which is now about 40-ish minutes, 42 minutes away. Then we have our third keynote by Sean White. And then lastly, you will not want to miss the awards and closing ceremony, where we have a chance to really acknowledge our best papers, general chairs, and look forward to future VR events. So please stay with us for another half day, get into Hubs, get on Slack, get social, and make the best use of the last pieces of programming that we've got for you. With that, this is, I guess I'm signing off. I feel like I'm a radio talk show now, but I've enjoyed chairing this session, and I hope that you all enjoyed the content as well. Take care.